Okay, I'll get started right away here. One of the things you'll notice here is I put why you're sitting at one of the most important moments in technical history. And this is something that came to me, I don't know, 2 weeks ago, I guess. And the reason I put that down there is we're watching robotics across the world change things very drastically. And up until now, what we've done is had robots take on very repetitive and known tasks. So robots can do the simplest things of putting a part from a bin, orienting it, and putting it into a car or something like that. But some new things have occurred this last year, in fact, the last few months, that have been changing this. So there was a machine that was just announced a few weeks ago where a robot can now custom stitch clothing. And this is a big deal because the trick was always to do clothing. It took a human hand, right, to stretch the material correctly and sew it. And it took a dexterous kind of a thinking and a feel for how the cloth moved and so forth. So now they've got a robot that can do that. So cheaper t-shirts are going to come. But it's really a bad thing in some ways too, because now the people who do that kind of labor, right, are, I don't know what we're going to do with them. So this is something to consider. And I put this out there because we're pushing robots in the ocean in the same direction. Right? They're taking over more and more complex tasks, doing things with greater dexterity that we really rely on people and people sitting behind desktops and so forth to manage. So I put that out there for you to think about. Now the other side of it is, you guys are the future of all this, and you're doing that work, which is really cool. So I'll start right away with some background. This is something I've talked about before with lots of people. I don't think I talked about it with you last year here. This is called Pasteur's Quadrant. I wish I had a laser pointer. We don't have one. If you look at this, on the one axis here is the quest for fundamental understanding. That's the business that I'm sort of in with scientists. At the bottom is this concept of consideration of use. And you see how they've placed some people in there. So Bohr was a physicist, and he looked purely at how to advance our knowledge and write papers and so forth, and that was his paycheck. Thomas Edison didn't really understand literature and so forth. He wasn't a big researcher and so forth. He just did things by trial and error. So he looked at the application of use. Pasteur was unique in his time, and I guess, well, maybe not unique, but he's the guy that gave this to. He actually looked at both and worked with both. He had a very methodical research method against his application and created, pasteurizing milk. And so this is where we kind of want to go, I think, with the work that you guys are doing. So recast that and how it relates to us. So right now, we've got this motivation, right, of hole in literature and so forth. So we're looking for, the science, what I do in my business, we're looking at ocean acidification, global warming, all those things that you hear about in the news. On the bottom side, right, is we're trying to do this exploration of these new theories and apply them. And that bottom quadrant, right, where you're in the deep immersion, integration of multiple theories, is where engineers exist. Most of you read books and get the theories from people and so forth, but you don't actually create those, right? You apply them. And there's nothing wrong with that, by the way. I'm not making you feel bad. But if you look, if we take both of those avenues and we take it up into this new theory and so forth, we actually have what they call a paradigm change. And this is where I think we really want to push robotics in ocean engineering. Right? We want to look at those equations also and not forget them, not take the easy stuff that's sort of laying in front of us, and maybe look at applying it in a way where we can actually shift things dramatically and in for the better, I hope. So I'm going to give you an example here. This is a bit of a stretch, so stick with me. So right now, this is an equation. Do any of you recognize it? Okay. He's hoping one of you smart guys might go, yeah, I know what that is. All right. But you live with this equation every day. Without this equation, a lot of the stuff that you guys do would never exist. The internet. Okay. So one guy did this purely theoretically. Had no application at all in mind. He just happened to sit down. He actually didn't do any experiments. He did it purely mathematically. Okay. I've even given you what all the parameters are there. So we'll answer this later, but I want you to think about how something that somebody did in pure theory, somebody took it through that application and took it to Pasteur's Quadrant, and it's impacted every one of you today. So we're going to go back to robots in the ocean now. Okay, so what science and industry robots, ROVs, remotely operated vehicles, do well? And these are the two that I work with at MBARI. So if you look, I use animals because they're charismatic, people like to fish. If I just showed you rocks and so forth, it's not so pretty. But on the bottom here, this is laser Raman, Insitu, and then there's an entire oil field down there and so forth. But some of these fish, that one at the top and that one over there on the far right, are two things that were discovered by MBARI. And I think between the two of them, there's some 10 million hits on YouTube or something. So they were that one on the right, everybody's known about anglerfish, but never seen one in situ. That only happened about 6 months ago. So they've never seen in situ alive before in film. So okay, so now ROVs do things pretty well. So why shift towards AUVs? This is the biggest driver here. There's lots of reasons, but I won't go into them. But this is it. If you look here, the cost of a ship and the staff to do these things per day is enormous, and it's growing. So to take out Alvin as a the manned submersible, I believe the daily costs right now are something on the order of $60,000 to $70,000 a day just to run for an 8-hour mission. So this is our costs here. So you can see that if you use our vehicle, right, the Dockworth, it's the big yellow one that I had up there, ROV, with our ship, and we're pretty cheap. You're looking at $42,000 a day if you want to borrow that from us. It's a lot of money. You buy a lot of AUVs for 42 grand. So that's the motivation, basically. So now I go back and I look at what I want to do, pushing that AUV out. And this is kind of a different spin on Pasteur's quadrant. But if you look, I've got task, complexity, and power. And power for AUVs is our biggest, really one of our biggest problems. We have unlimited power. We can do all kinds of things, make a lot of mistakes, spend time. But power is the big driver behind most AUV work. In fact, I think most of you here suffer this problem. Right? You've got to carry spare batteries. You can only go for so long. Batteries only live so long, and so forth. So you've designed your systems to be fairly power conservative. Maybe not for this competition. Maybe you burn a lot of power. It's a very short mission. But if you want to last long times, or you want to use smaller vehicles, power is a big deal. However, if you look and you watch how AUVs are growing into where the ROVs exist in the towed vehicles, it's moving at a pretty good rate. So that's green is where the gliders come in, and I'll talk about those in a minute. That dark blue is where about maybe a little over 5 years ago, 10 years ago, is the realm that AUVs were sort of stuck in. And now they're moving into higher power mapping things because we've improved the instruments and the vehicles and the batteries. We're doing sampling. We're certainly doing inspection. So that light blue area is where the AUVs have been moving into in the last few years. And they're starting to take over in very, very critical areas. I'm actually very surprised at how fast the oil companies and so forth are accepting AUVs. They're usually very conservative. So, but the cost factors are driving them. So I'll show you some examples of how these things look like when they're working. So this is the kind of map you get from an AUV. You cannot get this map from a ship right now. So because you can fly low and get in close, this is about 80 meters high above the bottom. You can get sub-meters resolution. Vertical resolution is something under 10 centimeters. I can actually get down to centimeter by centimeter pixels if I wish. I've done this. So you can do things with an AUV you really can't do. An ROV to do this same map would be $42,000 for months per day. You can't afford it. So I can get this map in 2 or 3 missions at maybe $10,000 a day or something like that. So very, very powerful tool. Same with inspection. All the pipeline inspections now, so where the oil companies have started, they're going into some other areas. But that Hugin vehicle, the big orange one there, has done the longest single mission pipeline survey accomplished to date. So it's completely acceptable, and that's not a Hugin top there, but you can see they get in right in close, they take a look, they take snapshot pictures of things that look like anomalies. They're very, very complex systems and do very, very high resolution studies. You can see here is a pipeline where it's been washed out underneath it, and so the AUVs caught that. Very expensive to get this other ways. Give you a little details on just the pipeline survey stuff here. So, and I've got 2 things I highlighted. One is this rapid onboard analysis. Okay, so now you can see these anomalies that actually will find leaks and store the data for you. The question is, why do you have to wait till it's recovered? So if we have subsea networks, that'll go away too, and that's coming. Right now, the reason you wait is you don't want to have a ship sitting above it, because then you're paying the same amount of money as if you had an ROV. Down here, the unknown burials. This is another one where the AUV is gathered intelligence, and so if you go along, sometimes the sands have shifted and so forth, and it buries the pipe. The AUV is smart enough to know how to do a search pattern and find when the pipe comes back out. If you used a human to do this, they'll do it okay, but the AUV is much faster and much more adept at it. In terms of sampling, this is where it started. There's now hybrids. This one actually was lost at sea last year. Do you guys know about Nereus? The deepest diving ROV AUV in the world. It imploded using these ceramic spheres. One of them cracked, and the entire thing imploded and went to the bottom. But for a couple of years, these guys were cat's meow. And you can see there's an AUV configuration and an ROV configuration where it did sampling. They use a fiber optic tether to do that sampling. So from the surface, you couldn't get to 11,000 meters with today's cable technology. So this is where this is going. So a battery-operated AUV that had an ROV mode. Use it. From there, new vehicles have been coming along looking at this. So this is another AUV that's done at Woods Hole. You guys know Hanuman Singh? Some of you may. Very, very nice guy. This one is going under the ice, and so it's equipped with an arm, and it's actually run acoustically instead of fiber optically. But the idea is, as it gets a little bit of learning and so forth, the camera can identify objects, it'll start grasping samples based on the program. So that's coming along. There's some stuff done by a guy named Connor Rajan called T-Rex, where the vehicle is going out and starting to make decisions based on environmental parameters. Say, this is what I want to look at. I'm going to shift my mission based on something interesting and so forth. The other thing AUVs give you is persistent sampling. You guys familiar with Argo floats? Okay. Argo floats are up in the front there, at the top right. They're an instrument pod, and they are an AUV. We don't call them that. We call them these buoys, but in actual fact, they are an AUV. They go up and down, they profile the water, and then they come up report that back by radio link. So there's 3,845 of them as of just a week ago, covering the entire Earth's ocean. This is how we know about the seas at the moment. There's more going in, and now they're starting to move into the Arctic waters also to get better coverage. These are tied. There's another image that has all the land stations, so they get a complete vision of the planet that we never used to have. Now, this, if you put a couple wings on it and make it tilt the other way, right? The guy who invented these, a guy named Russ Davis of Scripps, turned them into gliders. So I think you guys are all familiar with gliders as AUV people, but this is where they actually came from. So looking at persistence again, if you look to the left here, this is actually a typical sort of oil field kind of condition. It's not, the scientists can't afford this kind of equipment, or we would, but we do have subsea nodes and so forth that are going in that are scientifically based. If you look to the right, you'll notice that there's in-situ vehicles planted at the bottom. They're no longer run by ships from above. So there's two kinds. There's cabled ones, and then there's untethered ones. They go around and do specific missions. This has already been demonstrated in the North Sea. So these things are pre-planned to go out based on the sensors talking to them about what's going on with chemical flows and so forth, gas hydrate issues and so forth. They make automatic decisions, and then that vehicle at the bottom is a test unit of the one that's actually out in the field, and it goes out and actually does turn the valves and manipulate the entire system remotely, but autonomously. The other thing that's coming along, this is a vehicle that I worked on in a docking system with Jim Bellingham. There's several of these now. So the next generation of AUVs will stay in the water permanently. We won't have to have a ship at all. In fact, the Remus guys, if you've seen the smaller vehicles, they just launch them with two guys from the beach, pick them up. So you don't need a boat. But these are a little bit bigger. So these are now being planned. They're cost effective enough to leave them parked and let them do missions and so forth, and then just replace them on an annual basis versus weekly basis. So the next thing that I'm seeing happen is biomimetics. And this is an interesting field because I didn't actually believe in it much 20 years ago. I thought, I don't know, I just wasn't too up on it. But it turns out that the animals have developed a lot of skills and effort to maximize their work done for the effort spent. So a lot of guys are exploring this. And so this is a crab, kind of a looking unit. These ones have come a long way. These swimming fish. There's a fellow in Japan, Hayato Kondo, who built one that's called BA1. It's actually a big vehicle, and it feeds fish. So the fish actually school out to the vehicle. So he's doing open water farming. So instead of having the poisoning happen in fish farms and so forth, it's actually out in the natural sea and whatnot, and they follow it right back in. So it's still in the early developments and so forth. Down on the left here, at the bottom, that's actually a military vehicle for the U.S. Navy to do sensors, go into swimming places and whatnot, but be a little bit hidden. So we got a long way to go. So the top is, a lobster. The middle here is robo-lobster. And then the bottom here is somebody's conception of what it should be in the future. But I think this kind of thing is going to have a big presence in the future. In that, as we fish, right, we go out and look at capturing fish. Right now, we take everything. We're not very selective. So we're capturing all the small fish, and the ones that are required to restock and so forth. We hunt tuna like there's no end, and so forth. And I think that's not going to be sustainable. So I think these robots actually have a real play in helping us select and robotically fish in the future. Probably won't happen in my lifetime, but I think we're going to have to go there to make those resources sustainable. So then another thing I'm finding really interesting is swarms. In fact, Andar is on this. It's his research if you get to see it. And it's an interesting phenomenon why these animals do this and so forth scientifically. But I think this concept of schooling and clusters and whatnot will probably also play out as a big deal for us in terms of the future in sustainable oceans. And so that juvenile catch problem and so forth. Now these particular animals here tend to do it because of the environment. So they're sort of environmentally joined up. They don't go off solo. But there's a lot of things in school and whatnot. We have a choice to go off, choose to school for protection and whatnot. And that's why we end up catching everything as opposed to what we want. So, but some interesting things have happened on land. Like there's so many examples of swarms on land and on the surface of the ocean and whatnot in the air. Subsea, we're still very, very far behind. But that robot chain there on the right, the company that started that was a Willow Garage in Sunnyvale. And it's a little series of little robots. They don't really, no individual robot does much, but they self-cluster into new configurations based on the problem in front of them. So they'll create snakes to climb over things automatically. They'll create little towers to climb up things and whatnot. So they're looking at them for all kinds of things, like finding in earthquakes how to get through a building that's collapsed and look for survivors and that kind of thing. But the intelligence of them is kind of odd because no particular robot is actually smart. It's a collective. So it's a big shift in where we're going with these things. And I think the ocean is going to see a lot of this kind of swarming. This is a simple thing at the bottom, very, very simplistic, but these robots were given this image, and then they using a simple algorithm, completed the image. So I thought that was pretty interesting. So now, right, the question is, where we want to go with these vehicles? And this is one that I'm on. I talked about it last year, so I won't go into it too much. But not a new idea, by the way. The Soviet Union and the Americans had this idea of flying submarines many, many years ago. Cartoons have done it. But I think the technology is there now. In fact, I know it is. I've done the background work and I have my students working on it. But so you have a chance to build on this previous work. And the question to you guys is, what do you see for the future? You are the guys who come after us. You're the ones who come up with the next ideas. So I put that out there to you. I hope you're inspired carry on with these robots and have some fun. It's a great career. Do some really good work for the world. So now, you want to know about that first question. The answer to that is, it's one of the field equations from Einstein. So it's general relativity equations. And there was 10 of them. And this one, though, predicted the concept of stimulated emission. So the idea that you can take something, energize it and whatnot, and get photons out of it. So the idea of the LEDs. So all you guys right here, right now, love your LEDs. I know I saw a blue one peering through a window and blinking redwoods and green ones. Right? So without this equation, none of that happened. But the bigger thing is, without the laser coming from that, right, which was created by a guy named Robert Hall in 1960, we wouldn't have high-speed internet. So one guy in the 20s sitting there with a pencil and paper just thinking about the universe came up with these equations. Somebody found that equation, spun off on it and said, hey, I can make something glow and spit off light. Which is really funny because at the time he worked as a General Electric. I think the guys and the bosses all looked at it and said, well, that's a solution looking for a problem. What good is it? So that you're going to get that in your life. People are going to look at you and say, what good is it? And so forth. Don't back down necessarily. There's some common sense, but don't back down. Without that, without Einstein, without Robert Hall, right, all of our lasers, all that stuff, high-speed internet, fiber optic communications, and now I believe subsea communications, where we're seeing a lot of lasers used for some distance communications in the ocean, wouldn't happen. So I just put that out there to you. So here's the guy who did it, and he's like, logical will get you from A to B, and imagination will take you everywhere. So sometimes things are good, and profound, and you miss them early on. So just put that out there. Don't let yourselves get held back. You can do a lot of things. So now I'm going to take a quick sidebar. Our time is up. To talk to you real quickly about IEEE, the Ocean Engineering Society. There's a couple things specifically for you students. Now, all your older guys should be members too. I think there's a lot of benefit in it, and I think the societies as a whole have went through a swing where they sort of went down. People are like, I don't see the benefit and whatnot. There is a big benefit. And I think it's swinging back up. People are seeing it. But for you as students, two things. One, if you're an IEEE student member, you can get the application online, or come see me and I'll help you out. We have 8 undergraduate and graduate scholarships per year, 5,000 each. So I'll give you a big hint. We have never given away all 8 yet because we don't get enough applications. So it might be easy money. And that's the page you can go to on there. And I think whatever, you guys can get this link from any of the guys here locally. And the other one is the student poster competition that happens with our Oceans conferences every year. They happen twice a year. It's on the odd years, it's Europe, and on the even years, it's Asia. And then in the fall, it's spring meetings, and in the fall, they're always in North America. And in both of those, we have student poster competitions. You can get some travel money to get there if you're selected. And when you're competing, you're actually competing for cash prizes also. So you can make, I think the top prize might be $3,000 or $5,000 or something like that. But you also get some publication notoriety. The Journal of Ocean Engineering may contact you about your work, even if you don't win, and say, hey, we'd like to see that put into a full peer-reviewed paper. So there's some real advantages there for particularly the guys who are looking at master's and PhD type level work. So I'll leave it there for you guys and let you get on with your day and get in the water to play. Of course, I think we have to hear from all of you. So is there any questions from anybody?